Well, hello, good people. Welcome. Today we are talking about the Doppler effect and other related concepts. Now, when we talk about the Doppler effect today in this video, most of my videos I try to make pretty similar to what happens in the lectures. This will be kind of an exception. All of the physics will be the same. We'll discuss the same physics concepts, but it will not be in the same style as the lecture was presented in. So if you are rewatching this video to relive the lecture experience, unfortunately, I do have to let you know that this will not be that. That is an in-person experience only. What we are doing now is we are covering the concepts in a very talk about the concept sort of way. So if you are here to learn about the Doppler effect, then you're in the right place. Let's talk a little bit about the Doppler effect here. Imagine that I had a siren here that was sitting on the top of a fire truck. And imagine if the purpose of this siren was to go off to warn other people that the fire truck was coming. Probably not too hard to imagine. Here's my little siren. When this siren goes off, what's going to happen is that this siren is going to put out a sound at a very particular frequency. And when it puts out that sound at a very particular frequency, it's going to create a sound wave that's going to expand outward. And when I say sound wave that's going to expand outward, really what I should be saying is sound waves, because doesn't every sound wave have a bunch of compressions in it and a bunch of rarefactions in it, and then a bunch of compressions and a bunch of rarefactions? It goes compression, rarefaction, compression, rarefaction, compression, rarefaction. So what it will do is when the siren goes off, it will create a little compression. That compression will expand outward. Then it'll create a rarefaction that will expand outward. Then it will create a compression that will expand outward. Then it will create a rarefaction that will expand outward. And this series of compressions and rarefactions, the frequency of those compressions, gives you the pitch of the siren. So if we were to draw this on our paper, here's what we would draw here. We would draw...
I'm not sure I understand.
Yep, I'm sure you wouldn't, Siri. Okay, here's what we're going to draw. We're going to draw this siren. It's going to create a compression. That compression is going to expand outward, kind of like a ripple in a pond, but in 3D space. And it's going to make a giant circle around. And this is a circle of compressed air. Well then, after that, the siren is going to put out another compression. That compression is also going to expand outward, but it's going to expand outward right behind the first compression in a circle outward. Well, then it's going to put out another compression, and that next compression is going to expand outwards behind the previous circle, and then it's going to put out another compression, and that next compression is going to expand outwards behind the previous circle, and so on and so forth. So this could be a nice drawing or a nice illustration of a sound wave in which you see that these, let's change up our color here, the outermost circle here shows you the oldest or the first compression. This is your oldest compression here. And if you look here at the innermost, oh gosh, wow, that's not the innermost circle. Let's try again. If you look here at the innermost circle, that shows you the most recent compression. So you can see here that we have drawn a diagram that shows the sound waves created by a little siren as outward expanding circles, where each circle is representing one of the compressions. And the number of compressions that an outside observer would experience per time, if you had like a little person, if you had a little person standing here listening, ta-da! If you had a little person standing here listening, the number of compressions here that they hear per second will determine the pitch or the frequency of the sound that they hear. Now this is what you would see if that siren were sitting perfectly still. But what if that fire truck was on its way to go save lives? Huzzah! Here's what you would see. You would see here that the siren, instead of sitting still, would be moving. So here's what it would do. It would start here, and it would start by creating a little compression as it makes a sound. the little compression would travel outward in a circle. And actually, I kind of want to expand my circle here. The little compression would travel outward in I feel like I just made the exact same circle. Well, nope, we're going to try it again. I was going to say maybe it's meant to be, but no, I just do want it bigger. Okay, so it's going to make, that's a little bit larger. It's going to make a compression. It's going to travel outward in a circle. Well then, suppose that this little siren is moving along. If it's going to go help save the day, perhaps it's moving this way, is the direction of the little siren, then what would happen next is that the siren would move forward again, or it would move forward, and as it moves forward, it's going to make another compression. But now the compression isn't going to come from here. Now the compression is going to come from right here because the siren has moved. And so what you'll see is that the resulting compression is now going to expand outwards in a circle, but it's going to expand outwards in a circle with this little siren right here at the center. So you're going to get a new circle for the next compression that looks kind of something like this. Now, if that siren were to move forward again, because it's continuously moving forward, by the time it put the next compression out into the world, it would have moved forward a bit. And so now the new compression is going to move out in a circle, but that circle is going to start at this new location of the siren. And so the circle, the compression, is going to look kind of something like, well, that was a terrible circle. Let me just try that one again. Gonna look kind of something like this. So here's what you would see. Notice, do you see how on this side of the siren, if someone were standing right here listening, boop, doop, 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 boop. If someone were standing right here with their listening ears so attentive to sounds, what they would hear is they would hear the sound wave coming, and then whoa, the next compression would come, and then whoa, the next compression would come way super fast. They would hear a higher frequency because they would hear these sound waves all squished together. Notice, the siren is chasing after its own sound waves. And so the sound waves are going to come to this person way closer together, way more squished. They're going to hear more compressions per second. Meanwhile, this little buddy over here, when he's listening to the siren, he sees the siren moving away from its own sound waves. So the sound waves are moving back towards him, but the siren is moving away. So the sound waves, the little compressions, get to him more spaced out. So he would hear sound waves at a lower frequency. He would hear less compressions per second. So this little buddy over here would hear a higher frequency. He would hear the siren at a higher pitch. This buddy over here would hear it at a lower frequency because the sound waves would look more spread out. This is what we call this effect of a motion of something, the source of a sound moving as it creates a sound, is what we call the Doppler effect. This setup right here is the Doppler effect. And it happens when the source of a sound is moving as it creates that sound, or when an observer of the sound is moving towards the sound. Now, you've heard the Doppler effect before. And when I say you've heard the Doppler effect before, I don't mean that you just heard of the Doppler effect. I mean you have heard the Doppler effect, because it sounds like this. It sounds like when the siren of an ambulance or of a fire truck is coming towards you, it sounds one way, but then once it passes you, it sounds another way. It sounds like this. Like that. It starts out at a high frequency, and it starts out at a high frequency because when the siren is approaching you, it's creating a higher frequency here of sound as it chases after its own sound wave. But then after it passes you, you can hear the siren drop to a lower pitch. Why? Did the sound actually change? No, the siren's still putting out the same number of compressions per second, but the way that they're reaching you is different now because the siren, the creator of the sound, the source of the sound, is now running away from its own sound waves as it's making them. and so you would hear a lower pitch. You hear this with the race cars at NASCAR that go, meow. Same thing. You hear it as a high-pitched sound at first when it's coming towards you, then as a low-pitched sound as it runs away. The Doppler effect can happen with sound, but it can also happen with light, too. We haven't really talked much about frequencies of light yet, but we will soon. And when we talk, here's a little sneak peek for you. When we talk about frequencies of light, we will talk about how frequencies of light that are colors like blue or purple are lower, that was almost a disaster, are higher frequency colors. Meanwhile, colors like red or orange, those colors are low frequency colors. So we see that with a sound wave, the frequency determines the pitch. But with a light wave, the frequency determines the color of the sound. And blue colors are higher frequency and red colors are lower frequency. Now here's a true story, is that one time all the astronomers were looking up the sky and they noticed that all of the stars looked a little bit more red than they should look. And all the astronomers said, "That's very interesting. Why does it look like we have a red lens on all of our telescopes? Like it looks like all the stars are red for some reason, more red than they should be at least." Well, here's what they said. They said, if we're seeing that all of the stars look a little bit red, it looks like their frequency is just a little bit too low. Which means, according to the Doppler effect here, all of the stars must be moving away from us. They thought this was very interesting, and they didn't call it the Doppler effect because the Doppler effect, they said, applies to sounds. And they said, this is about stars, so we should give it a new name, even though deep down it's really rooted in the same fundamental concept. And so they called it red shifting. They said all of the stars in the sky are redshifted, which means that their frequencies look a little bit lower than they should. They look a little bit more red than they should. They said, this is very interesting. I wonder why this is taking place. And this was the first piece of evidence that we had where we really started to think, I wonder if the universe is expanding. That would make sense, because if everything is redshifted, then the stars must be moving away from us. And if the stars are all moving away from us and moving away from each other, they must all be spreading out. And if everything's spreading out, well, we call that expansion. And so the redshifting of all the stars was one of the major pieces of evidence for the expansion of the whole universe. So there's a little on the Doppler effect. Next, I'm going to show you what happens if the siren started to go really, really fast. What if, and this happened more with planes, so I'll kind of explain this with the siren, but then we'll talk about how this happened with planes. What if the little siren from the little fire truck had to go really, really crazy fast? And so the fire truck started driving along down the way at a super, super crazy speed, like super, super fast. Let's say that the siren was traveling at the speed of the sound that it was making. So what happens here is that the siren would create a sound wave. It would create a little compression. This little compression would expand outwards in I need a bigger circle. Let's be so for real. Shall we start over and make a siren more centrally located and then make a much bigger circle? Okay, let's try it. Thanks for that resounding yes, by the way. I really appreciate your engagement with the video. Okay, here we go. So let's say that this siren makes a compression. That compression is going to expand outwards like this. Then the siren moves forward, but it moves forward so fast that it moves at the speed of its own compression. So the next sound wave that it's going to make is going to overlap with the previous sound wave. I'll show you what I mean here. Let's say that the siren moves forward crazy fast, and so now when the siren makes its new compression, it ends up right here. Like that. Then let's say that the siren moved forward one more spot. So now the siren's going to move forward to right here. What would happen then is that the siren would make another compression, and that compression would then expand outwards like this. Check out what we have here. If the siren is moving as fast as its own waves, it's going to create a ton of constructive interference right here. And that constructive interference is going to lead to the stacking up of all of those waves, and it's going to create what we call a wave barrier. Think about it, instead of thinking about it like a siren, think about it like a little water bug hopping across a pond. Let's say that you had a little water bug right here, and then that little water bug hopped across the pond, but when it hopped, say that it went so fast that it hopped all the way on top of its last ripple. So here's a little water bug. This little water bug has made a little jump on the pond. When it makes a little jump on the pond, every time it jumps on the pond, it makes a ripple that goes outwards. Let's say it jumps on the pond, and then let's say it jumps, and as its ripple is expanding outwards, so as you have this ripple that's expanding outwards, right when it gets to here, the water bug jumps again and lands on top of its own ripple. Well, then what would happen is that the water bug made a ripple that started right here. Now the water bug made a ripple that started right here. In other words, the ripple that the water bug just made started on top of the previous ripple. Now if the water bug jumps to right here and it jumps on top of its own ripple again, now the water bug has started a new ripple in the pond that lands on top of its previous ripple, which had already landed on top of its previous ripple. And so you get a wave that adds on to another wave, that adds on to another wave, and you get a ton of constructive interference here. This creates a wave barrier, which is literally a giant wave made up of adding all of these little ripples together. Now, in order to make this thing, you have to actually travel this way, or I should say the source of the sound has to travel at the same rate as the wave. So it has to travel just as fast as the wave is traveling. This became a huge issue, not with little bugs on ponds, but with jets, fighter jets that were trying to go the speed of sound. Because here's what would happen. Is the fighter jet, every time the fighter jet moves forward, maybe I should get a camera up here so then you can see me big. Boop. Come on. We got it. Yes. Camera. Let us allow it to load. Any second now, it's gonna load, it's gonna be awesome, it's gonna be so great, it's gonna be super glitchy, it's gonna be fantastic. Okay, here's the idea. As the fighter jet was moving forward into the air, what that fighter jet was doing is the front of the fighter jet compresses a little bit of air right in front of it. Normally, if the fighter jet's going slow, it compresses that air, that compression of air travels forward, just like a little sound wave travels forward. That little compression of air travels forward, and the fighter jet follows back behind. But what if the fighter jet was going as fast as the compression? If the fighter jet was going as fast as the compression, the fighter jet would fly through the air. It would compress some air. That compressed air would move forward, but the fighter jet would be right behind. And as the fighter jet is right behind, it's compressing more air and more air and more air, but it's also chasing down its own compression. So the new compressed air just adds on to the old compressed air. And all of that compressed air builds up and builds up and builds up and builds up. And what would happen is when the fighter jets went as fast as their compressions, By the way, how fast does a compression travel through the air? Did you say 331 meters per second plus 0.6 times the temperature that day in degrees Celsius? Yeah, compressions travel through the air at the speed of sound. So what would happen is, every time one of these fighter jets approaches the speed of sound, gets right up close to the speed of sound, they would start chasing after their own compressions. And when they chase after their own compressions, they make new compressions that add on to the old compressions because the old compressions haven't moved ahead. The old compressions are still here. So they make new compressions add on to the old compressions, and you get a wall of compressed air that forms. This wall of compressed air that formed is what we call the sound barrier. And for years, we couldn't break through it because it's crazy, crazy compressed air. It literally, if you were in one of those fighter jets, you would say, it feels like I'm running into a wall. There's no way to get through it. Well, eventually, we just built fighter jets that could get through really intense walls. And when we did that, we pushed through the sound barrier, and finally, the fighter jets could go faster than the speed of sound. Once they made it through that sound barrier, it wasn't really that hard to keep going because now there was no wall in front of them anymore. But it was incredibly difficult to make it up to the wave barrier and incredibly difficult to make it through the wave barrier. After that, airplane just cruising through. As you can see, if you look here, if this were actually a siren and not a water bug, well, the siren would have to be moving at the speed of sound to get into this kind of situation where it's making a wave barrier here. So this doesn't normally happen when you have fire trucks because most fire trucks don't go about 750 miles an hour, but it definitely happens when you have planes. Let's talk a little bit about what happens if you go even faster. Okay. If you had a source of a sound that was traveling not at the speed of its own wave, but even faster than the speed of its own wave, well, first, it would have to break through the wave barrier to get there. But once it broke through the wave barrier, then it's cruising on its way. Let me show you a picture of a source of a sound that is now going even faster than its own wave. Let's look at our little siren again. Now I know what you're thinking. You're thinking, Miss Wilson, what is this lecture? A siren that goes faster than the speed of sound? Yep. Here it is. Let's say that this little siren can go faster than the speed of sound. Here's what you would have. You would have at first, this little siren creates a little compression, just like we're used to. That little compression is going to travel outward in a giant circle around the siren. Then the siren moves forward. It jumps over its own compression before making the next compression. So by the time the siren makes the next compression, it is ahead of its previous compression. Let's say that it ends up over here. So as this giant compression is traveling outwards, this sound wave ends up over here. When it ends up over here, it creates a new compression. That new compression expands outwards in a circle around. Oh no, that is a terrible circle. Try that. That's a slightly better circle, but I still don't love it, so I'm going to try one more time. Oh gosh. I'm so sorry. Okay, just stick with me. I can make a circle. I can make a circle. I can make a circle. Okay, well, you know what? We're just going to go with it, okay? So pretend it's fine. Okay, so the siren then makes another sound compression that travels outside. Well, then it jumps over its own, or I should say it speeds up so that it speeds up past its own compression before making the next compression. So by the time it makes the next compression, it's already ahead of its old compression. It's all the way up here. Oh gosh, this is just My circle drawing abilities are embarrassing. Okay, and then the siren moves on ahead past its own compression, and by the time it makes the next compression, it's ahead of its old compression, like right here. And it's going to make a new compression now. So now it makes a new compression, and that new compression expands outward in a circle kind of like that. Again, terrible drawing, truly awful, but you kind of get the gist. Imagine all these circles are perfect, and imagine that the little siren is located at the center of each of its circles. Okay, now here's what would happen. If that wave were traveling, or if that little siren were traveling faster than the speed of its own compressions, if it could beat its own compressions forward, here's what you'd get. You'd get that these new compressions are going to have a few places where they interact, like right here for one, and right here also, and also right here, and also right here, and also right here, not to mention right here. You'd get all these places where the old compression, or where the new compression is interacting with the compression before it. And then you'd get a place where that compression is interacting with the compression before it. And at those places, you would get constructive interference. You'd get a little compression stacked on top of a little compression. And what you'd get is you'd get a line of constructive interference here and a line, oh gosh, take two, a line of constructive interference here, going backwards away from the source of the waves. Now you say, Miss Wilson, this is a totally ridiculous example. There's no such thing as a fire truck that has a siren that goes faster than its own waves to make these compression walls like this. But there are examples of things that do these kinds of things. If you see a wave like this that's in 2 dimensions, it's called a bow wave. This is what we call it when we see it in 2 dimensions, like on the surface of the water. If you saw it in 3 dimensions, like in the air behind a fighter jet, we would call it a shock wave. If you saw it in 3 dimensions. If you've ever been wakeboarding before or water skiing before, then you have seen a bow wave behind the wake of a little boat. Here I shall draw, or I should say it is the wake of a little boat. Here is a little speedboat. Yay! There it is. If you've ever looked behind a little speedboat before, you'll see that there's this weird wave shape that comes out kind of like a cone from the back of the boat. That wave shape is a bow wave. That's what the wake behind a boat is. It has this place right here that's a place of constructive interference, and so you get a nice big wave here on the side. Then you get another place of constructive interference right here, so you get a nice big wave on the side. And it happens because the boat is traveling faster than the ripples that it makes in the water. So the boat ends up making a shape like this out the back of the boat. When fighter jets could finally go faster than the speed of sound, they also made this kind of shape out behind them. And so you'd have this fighter jet that's traveling like this, going much faster than the speed of sound. Well, then you'd have this wall of compressed air back here. This actually wouldn't be in 2 dimensions. It'd be more like a 3D cone coming off the back of the fighter jet. But you'd have these places here where you'd have constructive interference, where you'd have a super, super serious compressed wall of air. Well, if you had little people who were standing down on the ground, like right here, with their little listening ears open, as this fighter jet was going above them, the fighter jet would be going this way, and likewise the wave would be going this way. Hey, when this wall of compressed air got to this little person's ears, could they hear it? You betcha! Isn't that all that sound is just compressed air? So when this compressed air got to this listener's ears, this listener would hear a sound. And because it's a lot of compressed air, it would be a very loud sound. The sound that they would hear is what we call a sonic boom? You might have heard a sonic boom before. If you've ever seen the fighter jets that fly over the stadium and then heard the giant sound that comes after them, you always learn, well, you see the fighter jets first because they're going faster than sound, and then you hear them. What you're hearing is the wake. You're hearing the shock wave that travels back behind the fighter jet. Now, a very common misconception and something that I used to think that a sonic boom happened, and it was a very, very loud sound that happened right when a plane broke through the sound barrier. And it happened one time, and it was a one sort of event, a one sort of sound. And so I thought that they just perfectly timed all these things so that the fighter jets would break the sound barrier right as they drove over the stadium so that everybody could hear it. But that's not true. That's not how a sonic boom works at all. A sonic boom is not one sound that happens one time. It's this giant wave that follows back behind a fighter jet and sweeps across the ground. If you had a person standing right here, and another person standing right here, and another person standing right here, as this plane moves across the sky, this wave would sweep across the ground. First, it would hit the ears of the first observer, and they would hear the sonic boom. Then this wave would get to the ears of the second observer, and they would hear the sonic boom. Then it would get to the ears of the third, and they would hear the sonic boom. Finally, this wave would sweep past the ears of the fourth observer, and they would hear the sonic boom. A sonic boom is not one sound that happens one time when you break a sound barrier. It's this continuous sound that everybody just hears once when it passes by them. If the sound wave were to travel across the whole nation, everybody across the whole nation would hear it. It's not a one moment kind of thing. It's a continuous sound that everybody hears once when the wave passes by them. That's a little bit about a sonic boom. Now, I always like to ask my students, hey, if you were a little pilot sitting here in this little plane, this little plane right here. Talk about artistic talent. If you were a little pilot sitting in this plane, I like to ask my students, when would they hear the sonic boom? Well, kind of never. They wouldn't hear the sonic boom as they fly over because the sonic boom is back behind them. It's this whole region of constructive interference. So they would never hear it until, of course, they slow down, and then that sonic wave, that shock wave that's back behind them would have time to catch up with the pilot. But the pilot would not hear the sonic boom as he's sweeping over the stadium. To him, it would be totally quiet. Hopefully, you've learned a little bit about 3 things. First, I hope you learned a little bit about the Doppler effect. Which is what happens when the source of a sound is moving as it's emitting a sound. Second, I hope you learned a little bit about wave barriers and the conditions that have to be true in order to create one. When we talked about wave barriers, we talked about the sound barrier. And third, I hope that you learned a little bit about bow waves and shock waves. Which relate very nicely back to the wake behind a boat and the sonic boom that you hear when a fighter jet flies over the stadium. That's all for today, folks. I hope you have a wonderful rest of your day, and I hope to see you soon. Bye!